Hi friends, welcome back in this series of computer vision. So today we will see another topic that is on semantic segmentation. So basically segmentation is actually labeling or assigning a class to pixels, right? Although we will see the example in this case study. So again, before starting, please subscribe the channel. We need more subscribers so that our team will get motivated and we will keep making content like this. Now let's get started. So semantic segmentation using UNet. So this is basically about the data set that we'll be using. Now we are importing all the necessary libraries. So in this we have used the Colab 2.8.0 TensorFlow version. Now initialize the random number generator. So import random.seed0. Ignore the warning, so we can filter all the warning like this. Now loading the data set, as we are using Google Colab, so we need to mount the Google Colab, of course. So we have done like that. Now this was our project path where we had the image data set. Although I'll be providing the image zip in the description, link in the description as well, so you can check it out from there. Now as all our images are in the zip file, so we need to extract the content of these files. So image zip path, so taking the project path and the image.zip. Now from zip file, import zip file to extract all. So this way we can extract the zip folder, right? Now define the necessary parameter. So alpha is 1. So here with the hyper parameter for mobile net, that is these one, and higher width means more accurate but slower. So image width, image height, that means we will be using 224 by 224, right? This is the height of cells, width of cells, image size. Now train CSV, so this is the train CSV and this is the validation CSV, although we'll be providing the link for these as well. Now creating training data, so import numpy as np CSV, right? Then cv2. Now with open train CSV, so opening the CSV file. Now create an empty array for storing mask detail. Now y train, that we are going to store np.0 sum, one for line in file, height cells, width cells. Now print ytrain shape, so ytrain.shape, xtrain path, so we are defining the list. Now file.seek, right? Data is equal to csv.reader. Now reading this file, like from diameter as comma. Now for making a for loop, index row in enumerate data, for I are in enumerate row 1 to 7 and row 1 and row 1 7. Now row I plus 1. So this way we are making the loop and doing the necessary thing with the images. Like you can see that will be the path like this. Now we are splitting the to get the image, then we are replacing the path with the .jpg and .png. Now reading the image in form of vectors from here, right? Then what we are doing, changing the vector values to either 0 or 1. So this is done to mask the entire image data set. Now mask image, so this is basically resizing the image suitable for our algorithm. Then this is what this will help to segment the image with surrounding, right? That is different colors. Now remove a signal dimension entry, so we are doing it from here. So the link we can study it more from here. And if we print the ytrain.shape, so this is what we have, the ytrain.shape, right? Xtrain path, so we have this path here. Let's visualize some training example. So first example, so import matplotlib.pyplot as plt.imshow cv2. So first we are showing the normal image, then what we are doing is plt.imshow ytrain of 6. So the same image we have here, then the same image we have here. So you can see the segmentation of these pixels where the object was. So actually this is a cat, and each pixels that are filled with the cat, so these are assigned with a fixed class that we can say it as 6. Second example, again you can see the cat, that is 17. So if we see that, so how beautifully it has done the segmentation here. Now pre-process the training feature images and convert them into an array which is compatible with mobile net for our model. xtrain is equal to xtrain path. So from PIL import image. Now TensorFlow, we are importing preprocess input. So making a for loop, enumerating in xtrain path image, opening the image, so read this file, then resizing the image and converting into the RGB format, and then xtrain I preprocess input. So this will basically convert the image into float 32 array, right? Now xtrain is equal to np.array xtrain.shape. So this is the shape and all we have. Now creating validation data, like we have set the training data. Similarly, we are doing the same thing for the validation data. You can see that reading the image, doing the masking and freezing all these images from here, and you can see that we got the validation data in this way. Now let's visualize some validation examples. So plt.im show cv2 read x value path 6. So this is the sixth image this time, and you can see that this is the image of the cat that is segmented. Now preprocess the validation feature image and convert them into array which is compatible with MobileNet. So again, x value is equal to xval path. So again, doing all the thing that we have just done, and this is the x value shape we have. Now creating our own model now, right? So for that, of course, we are importing MobileNet from TensorFlow Keras application.mobilenet. TensorFlow Keras.layer, import concatenate convolution 2D, reshape upsampling 2D. TensorFlow.keras model, import model. Now define create model, trainable equals to true, model equals to MobileNet. Input shape, we are passing image height, image width, right? And include top false, alpha and weights is ImageNet, right? Then that means we are using ImageNet weights here. For layer in model.layer, so layer.trainable equals to trainable. Now block 1, block 2, block 3. So basically the convolution layer with so including all these 3 layer here. Now concatenating the upsampling 2D blocks 3 with block 2. Similarly concatenating upsampling 2D of x with block 1. Now x, so again the convolution 2D 1, kernel size is 1, activation sigmoid, reshaping it like we have done. We have defined the height cells and width cells, so same way we are using them. Define dice coefficient. So dice coefficient making the function, so we can directly call it numerator is equal to 2 into TensorFlow dot reduce sum y true multiplied with the y prediction. So denominator TensorFlow dot reduce sum y true addition with y prediction. Now return numerator, so numerator divided by this whole denominator plus the epsilon from the TensorFlow backend. Now defining loss function, so defining loss y true y prediction, so it will return the binary cross entropy, and here we have the y true y prediction minus this the backend log dice coefficient, and plus the TensorFlow Keras backend epsilon. Creating the model summary, so just need to model dot summary after doing the create model, right? So basically we are not creating, so we are passing create model false, then we are using model dot summary. So this is what the summary that we have here. Now compile the model, so define optimizer, define matrix and define loss. So first we are using the optimizer, so Adam learning rate that we are defining beta 1, beta 2, epsilon, decay and arm squared, right? So all these things, then you compiling the model, so loss equals to loss, optimizer, matrix equals to dice coefficient. Now defining all this callback, so from TensorFlow callbacks, model checkpoint, early stopping, reduce LR on plateau, so checkpoint, so again model checkpoint, so defining all the model checkpoint, then early stopping, that is monitor validation loss, patience should be 5, and reduce LR, so reduce LR on plateau, so monitor equals to validation loss factor equals to 0.2, patient 5, and minimum LR equals to this one, verbose equals to 1. So you can see here again we have the patience as 5 here as well. Now fit the model. So fitting the model by passing X-train, Y-train validation data. Epoch is 1, batch size 32, verbose 1. So in one epoch we have this validation dice coefficient as near to 60%. You can see the loss here, it is still 1.45. now let's do prediction on the model we trained. So basically this is the image that we have, and the n scale means we are normally holding the image into unscaled variable. Now image cv2.resize, so resizing the unscaled image on the basis of the image width, image height. Then feet scaled preprocessed input, so calling this function np.array of image, where the data type we are making it as float 32. Now prediction mask, so cv2.resize 1.0 into model.predict x equals to np.array feet scaled 0 greater than 0.5 image width, image height. So image 2 is image 2 is a prediction mask multiplied by image. So this way this will try to plot the image where with the semantic segmentations. Now if we see that, so here you can see that, but although we are getting a lot of noise, we can say, or the unwanted segmented part here as well, right? So in the similar one, another movie in the similar way in another image, so we are doing all these necessary thing and we are trying to segment it. So here you can see that again it could not solve this this area, right? Basically because we are interested in the object only. Now let's use pre-trained weights. So of course weights file equals to project path of this pre-weight or pre-trained weight, we can say. I'll also provide all these file in the link, so you can easily use them. Defining the threshold, epsilon value, model equals to create model, and model dot load weights file. Similarly we are doing the same thing with the pre-trained model, and here you can see that we have less bias than earlier, right? So the unwanted area is still here, but it is quite less with the custom one. Even with this image you can see that, and with this image you can see that, right? So of course the pre-trained model will these are trained with millions of data sets, right? And the annotations and all thing like that, so we can use that, but no harm to know it better, no harm to check it out, no harm to work around this. So I hope you enjoyed this video. If yes, please do like, share and subscribe. We'll be back with the next video very soon with some different content. Till then, all the best, have a good time, take care.